Okay, we're on to our second unit. In the first lesson, 2.1.1, we're going to talk about measuring position using percentiles as well as Z-scores, and we're also going to talk about cumulative relative frequency graphs. All right, so first let's get some vocab out of the way. You should write this definition down. We say that the pth percentile of a distribution is the value with p% of the observations less than it. So as an example, we have Jenny earned a score of 86 in her test. How did she perform relative to the rest of the class? So basically what we're trying to find is Jenny's percentile. So she got an 86. We can see her score right here. So that's the 86. And all of these people scored below her. So her score was greater than 21 of the 25 observations. So to compute the percentile, you would just do 21 into 25, which comes at about 0.84. So we would say that Jenny is at the 84th percentile in the class's test score distribution. So to compute percentile, find the number of observations below that specific observation and divide that number by the total number of observations. I'll write that out real quick. So all right. So student example, STEM plot below shows the number of wins for each of the 30 Major League Baseball teams in 2012. A, find the percentiles for the following teams. A, the Minnesota Twins, who won 66 games, so we'll find their percentile. That's the piece of data we're looking at. There are 1, 2, 3 observations below that. So to compute it, we're just going to do 3 out of 30, which is 0.1. So they are at the 10th percentile. All right, so that was the Minnesota Twins. Now let's do the Washington Nationals, who won 98 games. Let's see. 98. So they won the most games in the MLB that season. So to compute theirs, there are 29 teams out of 30 below them, which if you pop that in the calculator, comes out to about 0.97. So we would say that they are at the 97th percentile. And the Texas Rangers and Baltimore Orioles, who both won 93 games. So we find the 93. So 93. So those two represent the Texas Rangers and Baltimore Orioles. And so we'll count up the number of teams that are below them. So we have what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So both of them have 22 teams below them. So 22 out of 30. Throw that in the calculator. About 0.73. We're going to say both of them are at the 73rd percentile. All right, and that's it. So let's talk about what a cumulative relative frequency graph is. Sometimes these are referred to as ogive graphs, cumulative relative frequency, a little bit of a mouthful, but they are kind of what they sound like. So it displays the cumulative relative frequency of each class of a frequency distribution. So here I have a data table to kind of illustrate. And what we're looking at is the age of the first 44 presidents when they were inaugurated. And then we've broken this down into a frequency table, right? So there were 2 presidents who were between 40 and 44 years old when they were inaugurated. There were 7 from 45 to 49, 13 from 50 to 54, 12 from 55 to 59, 7 from 60 to 64, and 3 from 65 to 69. So what we've then done is taken that frequency and made it a relative frequency for each class. So each class, I took the frequency and I divided it by the total number of presidents to that point, which was 44, and that gave me a relative frequency, or a percent that fell into that class. All right. Cumulative frequency is kind of unnecessary. You don't need this column. But cumulative relative frequency is what we want. And so what we're doing to compute that cumulative relative frequency is stating the percent that fall within that class or lower. So the first class, presidents aged 40 to 44, we had 4.5% fall into that class. But the next class, what I want is not just the percent that falls in that class, it's 15.9. I want the percent that falls into that class or lower. So it's actually our 15.9 plus our 4.5, which gives me 20.5. So then for my class, cumulative relative frequency falling in the age group of 50 to 54, I'm adding, again, the previous 3 categories together. So it's the 29.5 plus the 15.9 plus the 4.5, and that's what's giving me 50%. And so we just keep doing that until the last class. It should add up to 100% because now you've covered 100% of your data. And now we're ready to actually make our cumulative relative frequency plot. So these sorts of plots will always look similar, meaning they'll always start down in the lower left corner, basically at 0. They'll always finish on the y-axis at 100. Because as long as you've gone through all your class lists, you should have accounted for all of your data, so it'll accumulate. The thing that will be different between these graphs is obviously the x-axis, depending on what data you're graphing, and then how quickly the curve gets to that 100. So some could be much steeper, some could be less steep, but they'll all eventually get to 100, right? And so the way that we graph them is you just put data points starting at 0, so from 40 to 44, I'm going to put my data point of 4.5 at 44, and then we just connect them with straight lines. So from 45 to 50, so then I would put my data point of 20.5% there, connect it with a line. 51 to 55, or sorry, 50 to 54 rather. Now I've accumulated 50% of my data. That one gets a pretty steep jump, and so on. So you're just plotting these, and it's kind of like a line plot. Connecting the dots. All right, so now I'm going to talk a little bit about how to interpret, and this is more likely the type of problem that you would see on the AP exam. They're not going to, I haven't seen one where they forced you to make one of these cumulative relative frequency graphs, but more they ask you questions and ask you to interpret one of these. All right, so here we're given the cumulative relative frequency graph showing the distribution of median household incomes for 50 states in the District of Columbia. And A, it says California with a median household income of $57,445 is at what percentile? Interpret this value. Okay, so you can see that our x-axis is our median household incomes, and they tell us that California has one at 57,445. So what I want to do is find 57,445 on the x-axis. That's going to occur right about here, right? Halfway in between 55 and 60. And we're just going to take that and draw a vertical line straight to the top until we hit the graph. Oops. Once we hit the graph, we're going to find that horizontal point of intersection, and we're going to draw a horizontal line till we hit the y-axis. Oh gosh, sorry. Trying to use a straight edge on my iPad, and it's not going super well. All right. Something like that. Then we're going to take note about what that cumulative relative frequency is. Mine's a little upsloping. I'm going to say it hits right there. Probably about 0.79. So what that means is that 79% of the data falls below this value. So we would interpret this as California is at the 79th percentile, which means in this case, 79% of states have median incomes below California. All right. What is the 25th percentile for this distribution? And what is another name for this value? So now we're going to kind of use the table in the reverse way. To find the 25th percentile, we would first find the cumulative relative frequency that lands at 0.25, which I'm going to say is right there. Then we're going to draw a horizontal line till we hit the graph. Right here. And we're going to draw a vertical line straight down. Right here. And it lands at 45. So I would say the 25th percentile is about $45,000. And another name we have for the 25th percentile is Q1. We also call that Q1. Okay, make a relative frequency histogram for this data. So this is an important one. You can kind of visually extract enough information to make a histogram from a cumulative relative frequency graph. The way to do it, they've already split these up into buckets for us, or into classes, right? We have class widths of 5,000, I suppose. So what we need to do then is just make the height of the bars in each class width. So for the first interval, the height of your rectangle will just be the height of that first point, like this. But for my second one, the height of my bar is not going to be the height of that second point, or third point, I suppose. It's actually going to be the difference between the second point and the third point. So I need to find that difference, that height there, right? And so that looks like it's a difference about, it's hard to say. Again, you're just estimating these. But that's the height. The height of this red line here is what the height of my second bar in my histogram should be. So I'm going to take it down just a little bit. All right, so let's make it right about here. Okay. You're going to keep doing that. The height on that class level that you're working on should be the difference between the 2 points that fall on that interval. Meaning the height of my bar on this interval should be the height of that red line. That's the vertical difference in distance between those 2 points on this ogive graph. So you kind of have to eyeball it. All right. Let's see. Okay, so about that high. Oops. So this is the height I want for this interval. So that's the vertical difference between those 2 points. So you can see kind of the steeper that section of the graph, the higher your histogram's bar would be. So this one's going to be much shorter. This one's about the same as that one was, I would say. And then my last one's going to be even shorter. About that. Okay, so that one's like the first one. All right, and there we go. So from the ogive graph, I'm able to sketch what my distribution looks like. So almost roughly symmetric, although there does seem to be a little bit of a right skew there, right? And so for part D, where is the original graph the steepest? I would say between 45 and 50, right? On the interval between 45 and 50. And that corresponds to the highest peak, right? Or the mode on my histogram. So the steepness of the ogive graph corresponds to the height of the bar on that interval. Steeper on the ogive means taller on the histogram. Less steep on the ogive, shorter on the histogram bars. All right, so now we're going to talk about another way to measure position within a distribution. So we'll do this with an example. Macy, a 3-year-old female, is 100 centimeters tall. Brody, her 12-year-old brother, is 158 centimeters tall. Obviously, Brody is taller than Macy, but who is taller relatively speaking? Meaning, relative to other kids of the same ages, who is taller? According to the CDC, the heights of 3-year-old females have a mean of 94.5 centimeters and a standard deviation of 4 centimeters. The mean height for 12-year-old males is 149 centimeters with a standard deviation of 8 centimeters. So given this information, so let me summarize that. So males had a mean of 149, so mean 149, and a standard deviation of 8, and then females, had a mean of 94.5 and a standard deviation of 4. All right, so before I get to this, let's talk about how we can compare. We're going to use these things called Z-scores, and this is what a Z-score is. It's also referred to as the standardized score. And that's what it does. It standardizes a data within a distribution. And the way you compute it is you take the datum of interest, you subtract the mean of its distribution, and you divide by the standard deviation. This tells you how many standard deviations a particular datum, that's just an individual piece of data, is above or below the mean of the data set. So if you get a positive value back, that means your datum is above the mean. If you get a negative value back, that means your datum is below the mean. So let's go back to that example. So the particular datum of interest for Brody is 158. He's 158 centimeters tall. So his Z-score, to compute that, we would do 158 minus the mean of his data set, which was 149, divided by the standard deviation, which was 8. Now, because the numerator is going to be in units of centimeters and the standard deviation is also in units of centimeters, one thing we see is that Z-scores have no units. That's why they're called standardized. It's just a value that tells you how many standard deviations above or below your mean a particular datum is in the data set. So if I do this one by hand, it's not too bad. I get 8 divided by 8, which is 1. All right, so Brody has a Z-score of 1 in the distribution of heights of 12-year-olds. This means that he is 1 standard deviation above the mean height, right? So he's taller. He's on the tall side. He's above the mean by 1 standard deviation. So now let's look at Macy. So she's a 3-year-old, so we want to compare her to other 3-year-olds. So her Z-score is going to be her particular height, which was 100 centimeters. So 100 minus the mean height for her age group, 94.5, divided by her standard deviation. So simplifying this one, 100 minus 94.5 is 5.5 divided by 4. So we get 1.375. So while Macy is objectively shorter than Brody, with respect to the distribution of heights, she's taller than her peers than he is to his peers, right? So she is 1.375 standard deviations above the mean in her distribution, whereas Brody is only 1 standard deviation above the mean. So we could say that Macy is taller relative to her peers. So I'm 6'4", which is pretty tall. My sister is 6 foot, which is tall for females, but she'll always give me a hard time because I guess there's a delineation called a person of height, and that means you have to be at the 95th percentile, and I'm only at like the 92nd percentile, even though I'm 4 inches taller than her, and she is, for men, I'm at like the 92nd percentile height wise. She's at like the 95th percentile. So she always brags that she gets to delineate herself a person of height, which I guess is a real thing, and there are like college scholarships based off of it. All right, moving on. So I'm going to have this be your student example. Go ahead and try it, and then we'll go over it in class. You can pause it here. The data is just home runs hit by 4 major league players from different eras of baseball. And you're also given the mean number of home runs hit in the league that year and the standard deviation for that. And so what you're going to do is compute a Z-score for each player so that we can see relative to their peers who was the best home run hitter. All right, pause it here. We'll go over this in class.